You've probably seen these equations before, but what do they mean visually? By the end of this video, you'll have a visual intuition for what these equations really mean.
Nice! But how does this translate to this equation? And how did you know exactly which arrows to use to create this pattern?
That's exactly what we'll see. But first, let's get into the context. The synthesis equation says that a periodic signal with finite energy over one time period can be constructed using a sum of infinitely many weighted, harmonically related continuous time complex exponentials.
Yeah,
We've also seen that given x of t, we can compute the weights of the complex exponentials using the analysis equation. Now, what do you think the synthesis equation looks like?
looks like.
Okay, let's consider this simple example and first visualize what its individual elements look like. We've already discussed that a continuous time complex exponential represents a circular movement on the complex plane. We've also seen that the nth harmonic moves n times faster than the first harmonic. The coefficients ak are the complex weights, and each harmonic is weighted by the corresponding complex coefficient.
So now we need to add these up to get x of t? That's crazy and hard to imagine.
Not if you consider the equation term by term.
Ah. Okay, a0 first then. That's just a complex number. So something like this?
Yeah. Now let's add this term.
Addition means stacking vectors head to tail. So we add a minus 1 to a0 like this. This vector needs to rotate in the clockwise direction with an angular velocity of omega. So something like this?
Yeah, exactly. Really good. Now let's try adding the next term.
Another rotating term, moving in a counterclockwise direction. Okay, we'll add up the weights as usual. Now let the rotations begin. Hey, it looks like Saturn.
Yeah. Also notice that although the vectors rotate at their own speed in their own direction, they're still connected to each other.
Aww.
Huh? Anyway, we could use the same procedure to add all these terms. First, we fix the starting position of each harmonic given by the complex coefficients and then begin the rotations. The path traced by the final arrowhead is our x of t.
Oh.
Now that the idea is clear, let's remove the circles. In 3D, including the time axis, we have something like this. Now, we could extend the same idea to include infinitely many terms using infinitely many arrows, each rotating in its own pace and direction, and yet they move together, connected as one, giving rise to x of t.
This equation feels beautiful now.
Yeah. So now you have an idea of what the synthesis equation looks like. Now let's visually derive the analysis equation. So now we are given the signal x of t. From its time period t, we can get to know the set of harmonically related complex exponentials that build x of t.
But we don't know how exactly to add them up.
Yeah. So now the aim is to calculate the AKs. Let's say we want to compute A1. So let's rewrite the equation this way. Visually as well, let's start with A1 and then add the other terms. And this makes no difference because
complex addition is commutative.
Right. Recall that we only know x of t. We need to figure out this structure of moving arrows. Okay, now what should we do to obtain A1 alone?
For starters, we could stop rotating it.
You're right. So which mathematical operation can help stop moving it?
Multiplication with the complex conjugate cancels the rotation.
Exactly. So let's multiply the whole thing by e power minus j omega t and see what happens.
Oh yeah, it stopped moving, but the vector corresponding to A0 started to rotate. Interesting. I did not expect that would change the shape so drastically.
Yeah. It's really amazing how each component contributes to building the entire signal.
Yeah.
So what should we do next?
It would be great if all these can simply vanish. Then we'd be left with just A1.
Actually, you're right.
What?
But how do we do this mathematically? Note that we have one component that is unchanging with time, the one we want to calculate, and the rest which are all rotating. We have with us t seconds of such signals. So now what can we do mathematically to eliminate these?
If we subtract the values of these signals at the beginning and at the end of the time period, we would get 0.
Yeah, excellent. But what about this?
Oh, even this would become 0. It would be nice if we could subtract in these cases but not in this.
That's actually possible.
What kind of fancy subtraction does that?
Integration.
Huh?
Let's consider integrating the two kinds of signals. We've already seen that complex integration corresponds to computing the areas under the real and the imaginary parts of the signal. So in this case, the areas cancel each other out because the underlying sinusoids have equal area in the positive and negative directions, giving us a value of 0. But in this case, we get the sum of these rectangular areas. So we get the desired value A1 scaled by the fundamental period t. So this is what we have.
So now we just need to divide by t to get AK.
Exactly.
Interesting.
Recall that in these cases, the integration is directly proportional to the subtraction of the values of the complex exponential at the start and at the end of the integration interval.
Hey, that's what I'd suggested.
Yeah.
Wow, this is really great. The same operation cancels the effect of the rotating components but retains the effect of the unchanging one.
Exactly. This is the beauty of orthogonal basis functions. If there was no way to entirely remove the effects of all the components except the one we want, we would not have such an elegant representation. Okay, so now if we want to calculate A0, what should we do?
This is anyway not rotating, so just remove all the rotating components by integrating over a single time period and divide by t.
Excellent. We see that each component contributes uniquely towards building the function. The information present in one component is simply not provided by the others. This makes the set of orthogonal basis functions an ideal choice to represent signals.
Are harmonically related complex exponentials the only possible set of orthogonal basis functions?
Great question. The choice of the basis depends on the nature of the signal x of t. So there are several basis functions out there.
Oh!
In the next episode, we'll explore another set of orthogonal basis functions for continuous time periodic signals.
Another one? What's that?
Think about it, and we'll meet you in the next one.